So a while ago we have the derivative, and we see that the derivative has a pretty nice geometric interpretation in that the derivative corresponds to the slope of the tangent line of the function. Now, last week we also see that the derivative is the counterpart of another operation called the integral. So you should kind of expect that the integral should kind of have some kind of pretty nice geometric interpretation as well. And it turns out that the integral corresponds to, what did I just do? The integral would correspond to the area under the graph. So whereas the derivative corresponds to the slope, the integral corresponds to the area. I'm just going to put that in a double quote, the area under the graph. So just so to say, let's say if my function is f of x, the area under this graph from a to b is going to be represented as the integral of f of x from a to b. So last week we talked about the general antiderivative. So the integral that we see last week are the one where there's no upper and lower limit on the integral. So this week we introduced this to kind of like a limit notation. So when your integral goes from a number to a number, it will correspond to the area under the graph. When I say area, it's not completely correct. The technical term, the technically correct term would be the sign area. Typically, when people think of area, the area should always be positive. However, when we do the integral of a function can sometimes be negative. So what it turns out actually compute is what we call the sign area. The sign area can actually be negative. In particular, the integral is going to be negative. So the integral is going to be negative when the graph lies below the x-axis. We're going to see that in a moment. So basically, when I say the integral corresponds to the area, the technically correct term would be the integral corresponds to the sign area between the graph and the x-axis. And the notation for that is the integral of f of x, and it goes from a to b. So that a thing and b thing is the new thing that we see in this week. So we're going to see how we can compute this area, this integral thing in a moment. Okay. To compute that, we will use what we call the fundamental theorem of calculus. In our practicality, this is basically one of the most kind of important theorem in calculus because it actually is what relates the derivative to the integral. It basically says this: if my big function f is the antiderivative of my little function f, then to find the integral or to find the sign area from a to b of little f, I can basically just compute the big function f and evaluate that at b and minus the function f evaluated at a, and that's going to give me the integral. That's going to give me the sign area under the graph of the little f function. So let's actually look at the example that should be make it a little easier to see. So let's say I like to integrate 2x minus 4. This is pretty straightforward. We see how to do that last week. That's going to be 2x become x squared minus 4 become minus 4x. And then, I shouldn't have this integral sign. And then plus a constant c. So this c is a constant, so it just means it can be any number. In terms of the fundamental theorem, we will have that my little f is 2x minus 4, and my big F is x squared minus 4x plus c. So my big F function is the antiderivative of little f. My little f is the derivative of big F. So this is straightforward. Now then, I would like to compute the integral of 2x minus 4 dx from 2 to 5. Now, I'm going to appeal to the fundamental theorem of calculus here. My little f, so just like what we have the earlier, my little f, that's going to correspond to my little f that I have pointed out earlier. My little f is going to be the 2x minus 4 function. So the fundamental theorem of calculus said that this integral is going to be nothing but my big F of b, which is 5, minus big F of a, which is 2. So that's where my 5 and my 2 come from. That's the limit of my integral. So to compute the area under this graph, to compute the integral from 2 to 5, all I have to do is compute f of 5, f of 2, and subtract them. So let's actually do that. I'm going to use my big F here for my computation. My big F of 5, that's going to be 5 squared minus 4 times 5 plus c. My big F of 2, that's going to be 2 squared minus 4 times 2 plus c. If I were to compute that, this is going to be 5 plus c, that's 25 plus 20. Minus 4 minus 8, so that's going to be minus 4 plus c. So in the end, the c would have been cancelled out. So I'm going to be left with 5 plus 4, which is a 9. So one thing we see that the constant get cancelled out here. But one thing I'm gonna point out here is that this is actually always happen. The constant always get cancelled out. It just so happens that your big F, when you have the plus c in here and plus c in here, it just always cancels out. So as we will see in the future, typically when we do the when we find the integral, the definite integral when it goes from somewhere to somewhere, we will actually just leave the plus c out, because eventually in the end it always gonna get cancelled out. So it doesn't matter whether or not we write them out. For the next part, I'd like to find the area between the graph of 2x minus 4 and the x-axis on 2, 5. So let's actually, this graph is a line, so it's pretty easy to draw. It's going to be the graph, it's going to intersect the y-axis at negative 4, and it's going to have slope 2. It's going to cross the x-axis at 2. So when it goes from 2 to 5, the graph looks exactly like this. So it's actually going to be just the triangle. The base of my triangle, you can kind of already see. the length of the base of my triangle, that's 5 minus 2, so that's a 3. What about the height of my triangle? The height of my triangle is going to be the function value at 5. So whatever that is, the function value at 5 is going to be 2 times 5 minus 4, so that's a 6. So that means the height of my triangle is exactly 6. So I have a triangle with base 3 and height 6. To compute the area, that's going to be just a half of 3 times 6, and that's going to be a 9. And we immediately see that this is the same number. So indeed, when we compute the integral, that actually gives us the area under the graph, at least in this case. Well, we know it's true in general anyway.